In this video, we will discuss measures of central tendency. So first, let's review a little bit about summation notation. Many formulas in statistics will involve adding up many items. Particularly, it will say, add up all the items in this list. Whenever we have repeated addition of items in a particular list or something that we can describe mathematically, we can use something called summation notation. In summation notation, we use this symbol, which is a capital Greek letter sigma, and it tells you to add up all the things that look like x. So what you can see here on the right side of this equation is we are adding up all the values x sub 1 plus x sub 2 plus next would come x sub 3 all the way up to x sub n. So here the subscripts, the things written in the bottom right corner of the letters, are indicating the order of the data item in the list. So for example, if I labeled all my data items that you now see on the screen as x, then the sum of all data values x would be the first data value 1, plus the second data value 1, plus the third data value, which is a 2, plus the fourth data value, which is a 3, and then continuing to add up all the data values in the list. So we would add these all together, and that would be the sum of all the data values. So the sum of all of these data values is the number 22. So that's a bit about summation notation. With this in mind, let's review the definition of the mean. Now, probably a phrase that we're more familiar with in terms of mean is the average. In order to find the mean of a list of data values, so here my x sub 1 through x sub n are just a list of data values. In order to find the mean of those data values, if there's n data entries in all, we could calculate the mean by adding up all of the data entries and then dividing it by the number of entries. And that's exactly what we see here. We see the summation notation telling us to add up all the data entries together, which is what we see on the right side of the equal sign, and then divide that by n, which is the total number of data entries. Let's practice this concept. A city issued the following numbers of building permits over a 6-month period of time. One of the months, there was 310 permits issued. Another month, 296, 240, 374, 198, and 280. From these 6-month period of time, we're asked to find the mean number of building permits given out over that 6-month period of time. So how many data entries do we have? We have 1, 2, 3, 4, 5, 6. So n, the number of data entries, is 6. In order to find the mean, we will add up all the data entries and then divide by the number there are. So we already know the number is 6. Let's add up all the entries together. So I'll take the 310, add that to the 296, add that to 240, add that to 374, add that to 198, and finally add that to 280. Now let's add these first values in our calculator, and then we'll write what that's equal to, and then finally we'll do the division. The sum of all the building permits over the 6-month period is 1,698. We'll now divide that by 6 to get our mean. And we find there are 283 building permits issued on average during the 6-month period of time. Another measure of central tendency is the median. Now, the median is useful to find because it is not so sensitive to what we might call extreme values or outliers. Instead, it will divide the group of observations into two parts, with half of all the data observations lying below the median and the other half lying above the median. So how do we find the median? First, we need to rank all the items and arrange them in order from least to greatest. So if you're given a data set and asked to find the median, do not assume that it's already written in order. You would have to check that first and then reorder it. Remember, if there's repeated data entries, you have to keep those repeated data entries and include that as you reorder the list. Step 2 is to find the number in the exact middle of the list. Now, if the total number of items in the list is odd, then there will be a unique middle item in the list. You can see what's exactly in the middle. However, if the number of items is even, there's not an exact middle entry. Instead, you have to take the average of the two middle items. So you'll find the two items in the middle, add them together, and divide by 2. Let's practice finding the median of a few different data lists. And a quick reminder is whenever we find the median, we must make sure the values are in order. If they're not in order, let's rewrite the list in order from least to greatest. Let's work on this first example. If you would quickly look through the list and identify, is it written in order? Because if not, we must first reorder it. Looking at the data entries, we see 6, 7, 9, 11, 15, 25, 33. Everything is numerically in order here. And one way we can work this out is, since it's numerically in order, I can find the middle item by slowly working myself towards the middle. I think about canceling the first and the last digit, canceling the next to first digit, the next to last, and we continue this way until we see that there's 3 items to the left of 11, 3 items to the right of 11. That makes 11 our median value. So the median is 11. Now as we turn our attention to the next example, let's briefly look through and see, is the list in order? Because we know median must have an ordered list. Here we quickly see it's not in order, so I would encourage you to pause the video now and rewrite this list in the correct order. Unpause to check your work. So as we reorder it, I always like to mark once I've used a number so I don't forget. I'm not going to cross it out because then it will be hard if I need to reference it later to see what it was. We can just do a dot above or below. 132 is the lowest entry. I believe that's followed by 147, which is then followed by 159, then 174, then 181, and finally 253. As we did before, let's find the median by just taking values from the left and right and slowly working ourselves towards the middle. We can do this because the list is now in order. And as we do this, we see we're left with 2 items in the middle. That's because there are 6 items in all. That's an even number of items, so there are 2 in the middle. So the way we find the median in this case is you add the 2 items together and then divide them by 2. This is finding the average of the 2 entries. So that value will be 166.5. That is the median value in our list. A third measure of central tendency is the mode. The mode measures which value occurs the most often. And one thing to keep in mind in terms of mode is that there could be no mode if all the values occur only one time. In that case, there's no value that occurs the most often. There could be a single mode if there is one data entry that occurs the most amount of times. Or there could be 2, 3, 4, 5 modes, etc., if there are multiple data entries that all occur the most times together. So in this next example, we have 10 students who earned the following scores on a history exam. We are asked to determine the mode score. So what we would do here is we would ask ourselves, do any of the data items repeat themselves? If so, do any of the items repeat themselves the most? Take a moment to glance through this list. We see that 74 repeats itself 3 times. And the remaining items are 81, 39, 82, 80, 100, 92, 85. None of the remaining entries repeat themselves. So in this case, our mode is 74 because it's the most commonly occurring data entry. So there is one mode in this example. In our next example, we're asked to find the mode for these data values. Look through the list and ask yourself, do any of the entries repeat themselves the most? As we look at this list, no entry is repeated. 10, 4, 5, 822, 100. None of those appear more than one time. So since there are no repeated data items, this implies that this data set has no mode. In this video, we will cover measures of dispersion. Our first measure of dispersion, which tells us how far out the data values are spread from each other, is the idea of range. The range of a data set is very easy to calculate. All we have to do is take the greatest value in the data set and then subtract it by the least value in the data set. So range is greatest value minus least value. Now in this next example, I have 2 data sets. The first one is data set A, and data set A has elements 5, 6, 7, 8, and 9. The next data set is data set B, and data set B has items 1, 2, 7, 12, and 13. Now one thing we can note about both data sets is they're both written in order. 5, 6, 7, 8, and 9. A is in order. And data set B, 1, 2, 7, 12, 13 is in order. So that can help us quickly find the range. We know the range takes the highest value in 1 and subtracts it from its lowest value. So the range will be 9 minus 5, which is 4 for data set A. And then to find the range for data set B, we will still take the highest minus the lowest. For B, the highest is 13 minus the lowest of 1, and that gives us a range of 12. Now let's find the median in both. We know to find the median, we look for what item is in the middle. Get rid of the highest from A, its lowest. Next highest, its next lowest, and we see 7 is in the middle. A similar process shows us that 7 is also the median for B. And then we know to find the final measurement, the mean, we would take the average of the data values. So to find the average for A, I would add up all the data values, 5 plus 6 plus 7 plus 8 plus 9. And as there's 1, 2, 3, 4, 5 entries, I would divide that by 5, and we would get 7. So the mean is 7. Let's similarly calculate the mean for B. And as you find the mean for B, I encourage you to pause the video and attempt it on your own. We know the mean can be found by taking all the data entries for B, adding them together, and then dividing by the number of entries. There's 1, 2, 3, 4, 5 entries. And when we do that, we get the mean is also 7. So we found the mean, median, and ranges for both distributions A and B. The next part of the question, we are asked to describe what the results imply about the different data sets. One thing we can note of interest is that data sets A and B have both the same mean and median. However, as they differ in range, the range for dataset B is significantly higher than the range for dataset A. So the range tells you how far the data values are dispersed, and we can see that in B there's quite a bit more variance. We have values ranging from 1 to 13, whereas in dataset A, the values are much closer together. They vary only between 5 and 9. So let's write down something close to that. The idea that while their medians and means are the same in both datasets, the data in B is much more spread out than the data in A, which is quite a bit more clustered together around 7. So we have the range of B is 12, and the range of A is 4. This large difference in their ranges implies the data in set B is more dispersed than in A. In the next example, we have a collection of quiz scores that Max and Molly scored. We can see Max's scores in the second column. Molly's scores are recorded in the third column. In this problem, we are asked to find the mean, median, and range. I encourage you to take the time now to pause the video and attempt this problem on your own. Calculate the mean, median, and range for both data sets, and then try to think about what those answers mean in terms of how we can relate the different data sets as we did in our last example. So pause the video now, unpause to check your work. So let's find the mean for Max. We know the mean can be found by adding up all the data entries and then dividing by the number of entries in the list. There's 1, 2, 3, 4, 5. And when we do that, we get 23 as the mean for Max. Similarly, we can find the mean for Molly by adding together all of her scores and then dividing by 5 as there are 5 scores. When we do that, we will get a mean of 23. Next, let's find the medians. Now we know in order to find the median, list out the data entries in order. Now these are not currently in order, so let's rewrite them. The lowest score was 18, followed by 21, followed by 22, followed by 26, followed by 28. To find the middle score, we go from the outer edges inward, and we see 22 as the middle score for Max. Similarly, let's reorder the list for Molly. Molly's score, lowest, was 6, followed by 3 27s, followed by a 28, and the middle of these scores was a 27. So that's how we'd find her median score. And then the range is always the highest score minus the lowest. Now for Max, his highest score was 28. And as we look, his lowest score was 18. So that's 28 minus 18, which would give us a range of 10. Molly's lowest score was 6, but her highest score was 28. So that gives us a range of 28 minus 6 is 22. And all that's left for us is to analyze these results. What does it mean about Max's and Molly's quiz scores? Now, just looking at Molly's scores, do we see, with the exception of that 6 quiz grade, or the quiz 4 grade of 6, her other 4 quiz grades are very tightly clustered around 27 and 28. So Molly has one big drop, but other than that, she's very consistent. Whereas Max's scores vary more between each other. We have an 18, a 21, a 22, a 26, and a 28. So the first thing we notice, Max and Molly have the same mean score. Their average score are both 23. Now let's talk about what the medians mean. Max's median of 22 means half of his quiz scores lie below 22, and half lie above 22. Whereas Molly's median score of 27 means half of her entries lie above 27 and half of her entries lie below. So half of Molly's entries lie well above her mean score due to the fact that 4 of her quiz grades are tightly clustered around 27 and 28, and then she kind of has an outlier of a quiz grade of 6 that pulls her average down. So this is really key here. Since half of Molly's quiz grades are greater than 27, the reason her average is 23 is that low quiz grade of 6 is pulling down her average. Okay. And we can see that based on the range. Molly has a much larger range of values, even though 4 out of 5 of the values are tightly close together. So our conclusion could be that in general, Molly is more consistent, with the exception of quiz score, which greatly affected her range results of being 22. Our next measure of dispersion is standard deviation. Standard deviation determines the deviation from the mean of the individual data values. Let's go through one example of calculating the standard deviation. So for our next example, we have the data items 32, 41, 47, 53, and 57. We are first asked to find the mean for the data values. We can do so by adding them all together and then dividing by the number of entries. There's 1, 2, 3, 4, 5 entries. And whenever we type this into the calculator, we will get 46. So the mean for this data is 46. Now we'll fill in this table. Now this is the table I would encourage you to always write on your scratch paper when you deal with standard deviation. So how is the table laid out? Well, it has 3 rows. The first row is the data value. Next is the deviation from the mean. Next is the square of the deviation from the mean. So you'd list out these 3 categories and then separate it into this column. And then what we're going to do is, based on the number of data values that were given, we fill in the table. So let's fill in our data values. First we have item 32, and I'll draw my line. Next we have item 41, then 47, 53, and 57. So notice in the first row, I've listed out all the data values. So next up, we need to calculate the deviation from the mean. And your formula for the deviation from the mean will always be the data value minus the mean. So to figure out our entry here, I would take the data value of 32 minus the mean of 46, type that into the calculator, and we get the deviation from the mean is negative 14. And then we continue this for the remaining entries. So for the next one, I would take the next data entry of 41. I'd subtract the mean of 46, and we get negative 5. Continuing, I take the data entry of 47. I subtract the mean of 46. We get the deviation as 1. Next, I take the data item 53, subtract the mean of 46. We get the deviation as 7. And then finally, we take the data item 57 minus the mean of 46, and we get the item 11. Next up comes the final entry of this table, the square of the deviation from the mean. So in this case, you're going to take each item you found in the second row and square it. So negative 14 squared. Now, any number, when squared, is a positive number, but if I want to verify, I can type this into my calculator. Negative 14 squared is 196, so that's what I'll list there. Now negative 5 squared is 25, 1 squared is 1, 7 squared is 49, and 11 squared is 121. And again, where am I getting these values? I'm taking the entry and I'm squaring it. Now the final step, which will be described in our next page of notes, is that step 4, we've squared the deviation. So next we will add all of row 3 together. So we imagine taking 196, adding that to 25, adding that to 1, adding that to 49, adding that to 121. Type that into our calculator, and we get the value 392. And then the next step in finding the standard deviation is you now take this value and we divide it by n minus 1. Now in this section of notes, remember n is the number of entries. So earlier n could be calculated 1, 2, 3, 4, 5 entries. But we do not want to divide it by n, we want to divide it by n minus 1. So now I would take the 392 and divide it by 4, because it's 5 minus 1. That's 392 divided by 4. And that gets us the value of 98. And we're almost at our final step. The last thing we would need to do is take the square root of 98. And when we do, we see that's about 9.899. Now, why do we go through these steps? This was to find the standard deviation, and this was just our first example. We have quite a few more examples to follow this. So let's now go and review the step-by-step instructions of what we just did written out on our next page, and then we'll do more examples of this topic. So these are the steps to calculate the standard deviation, and I do want to let everybody know that all of these steps will be given in this related chapters exam. So you do not need to memorize these steps, you just need to know how to work with them if they're provided. So let's read through these together. Suppose we have a data set of numbers x sub 1 all the way up through x sub n. So there are n entries in the list, and we could calculate their mean. Then what's called the standard deviation, denoted with S, can be calculated by this formula. Now, I think this formula looks rather complicated, so instead of talking through the formula itself, I've written out the steps that you would need to do in order to make the formula work, and if we follow the steps, we'll be able to calculate the standard deviation. What is implied in this formula is that you first calculate the mean of the numbers. So step 1, calculate the mean. Then step 2, you find the deviations from the mean. This is what we did in our table right above this example. We said how far is each number away from the mean, and we recorded that in the table. That's step 2. Then, once you found each of those deviations for each of the data items, you square the deviations. Then, you add together all the things that you just found, which we did before. And then finally, the key thing we have to keep in mind is we divide this number not by n, but by n minus 1. So watch out for that. The most common error here will probably be dividing it by n instead of n minus 1. Then finally, the last step is to take the square root of what you just found in step 5. So keep this portion of the notes visible, and let's go to our next example. In this example, I'm asked to find the standard deviation for this list of data. Now, in order to organize our work and help us get the answer correct, I encourage you to always draw the following chart with your standard deviation questions. always start with a 3-row chart where you list out the data values, then list the deviation from the mean, then list the square of the deviation. Now let's begin filling in this table. First, list out the data values. We have a 7, 9, 18, just reading off the list, 22, 27. So we've listed out all of the data items from the list, and next we need to calculate the mean. So remember, to find the mean, you add all the data values together and you divide by how many entries there are. Let's count the number of entries. 1, 2, 3, 4, 5, 6, 7, 8. So my n is 8. Now I'm going to add all of these numbers together and divide by 8 for my mean. And when I add them all together, I get 184. Divide that by 8, and we get a mean of 23. Now to find the deviation from the mean, we know we always take the data value and subtract that from the mean. 7 minus 23 will give us negative 16. 9 minus the mean of 23 gives us negative 14. And let's continue to fill in this chart. So we found all of the deviations from the mean, always data value minus the mean. Next, we square each of these values. So we square negative 16. Negative 16 squared in your calculator is positive 256 because that's negative 16 times negative 16. Negative 14 squared, which is negative 14 times negative 14, is 196. Negative 5 squared is 25. Negative 1 squared is 1. 4 squared is 16. 6 squared is 36. 9 squared is 81. And then 17 squared, if you type it in your calculator, is 289. Now let's briefly look at our list of our steps for the standard deviation above. Let's review which aspects of these steps we've completed. We have calculated the mean. It was 23. We found the deviations from the mean. That's what we did in this row. We squared each deviation. That's what we did here. So what's up next? We need to sum the squared deviations. So we will add together all of these numbers. So imagine writing in a plus for each of these. So let's add these numbers together in our calculator. And when we add all of these together, we get 900. So we're done with step 4. Now, step 5 tells us to take this number, 900, and divide by n minus 1. Now our n was 8, so n minus 1 is 8 minus 1, or 7. So next we'll take the 900, divide that by 7, and we get, rounded to about 3 decimal places, 128.571. That's step 5. And then finally, the last thing that we have to do is what we just found in step 5, we need to take the square root of it. So I'll take the square root of this number, and I find that the square root of 128.571 is about 11.339 when rounded to 3 decimal places. And that is how we would calculate the standard deviation. Our next example asks us to find the standard deviation of this sample. So we see we've got the data items 13, 14, 17, 19, 21, 22, and 25. Always whenever we're asked for standard deviation, we think, I need to make the correct chart that helps me. What is that chart? So whenever we are asked about the standard deviation, we immediately should write down this table to help us structure our work. The first row is always the data values, the second row is always the deviation from the mean, and the third row is always the square of the deviation from the mean. So this needs to be always part of our process when calculating the standard deviation. Next, we start to fill in the chart, starting at the first row. What are the data values? Well, we can see them above. They are 13, 14, 17, 19, 21, 22, and 25. Next, before we can find the deviation from the mean, we need to know what the mean is. So in calculating the mean, we first count how many data items are there. 1, 2, 3, 4, 5, 6, 7. So n is 7. We know the mean will say add all the data items together. So in our calculator, let's add these together, and then we'll divide that by 7. Whenever we add all the values together, we get 131, and then we'll divide that by 7, and we get, when rounded to 3 decimal places, about 18.714. So this is our mean. Now, in following the steps of the standard deviation, is we first complete the table, and then we have to add those few additional steps. But let's complete the table first. The deviation from the mean is always the data value minus the mean, so this will be 13 minus 18.714. We need to type this into our calculator to figure out what it is. And we get negative 5.714. And in terms of our quizzes or exams, if you're asked a standard deviation problem, I will tell you in the quiz or exam how many decimal places to round to within the problem. So let's say for this problem, we were told to round to 3 decimal places. So let's make all our calculations to 3 decimal places, and that will be told to you within the problem. So next we have the data entry 14. How far is it away from the mean? Well, we subtract 14 minus the mean of 18.714, and in our calculator we would get negative 4.714. Now, if you are getting the hang of this, you can just type this into your calculator. You don't have to write out the subtraction. So for the next one, it would be 17 minus the mean of 18.714, and that gives me the value negative 1.714. I'd encourage you to pause the video now and complete the rest of the second row. Unpause to check your work. And we get the following values as the deviations for the mean. Now, what do you do for the next row? You just square each of the entries you found above. So for the next entry, I'll take my negative 5.714, type that into the calculator squared, and we get this value. Now, we were told to round to 3 decimal places, so we'll round that as we look at the 9. Past it is the 7, so we round up. So let's round this to 32.650. And then we'll continue to square each of the entries, so negative 4.714 squared. And we get this number when rounded to 3 decimal places, 22.222. Now, if you feel like you've got the hang of it, I encourage you to pause the video, attempt the rest on your own, unpause to check your work. So at each next step, we take the previous square of the deviation from the column above, or the row above, and then we square it. So we type this into our calculator, and we get this number. When rounded to 3 decimal places, it's 2.938. Continuing, we get this value when rounded to 2 decimal places, or 3. Next, when we square this entry, we would get this value rounded to 3 decimal places is 5.226. Continuing, let's square this value, and we get 10.798 when rounded. And then finally, we will square the last entry, which when squared is 39.514. So we finished constructing our table, and now if you look back at our steps to writing the standard deviation, the next thing that we have to do is add up all of the values we just found on the third row. So imagine adding these together, carefully typing them into your calculator to not miss any decimal places. And when we add all of these together, we would get, let's calculate it separately and check each other's work. And we get, when all added together, 113.43. Okay, the next step is always to take the number that you just found and then divide it by n minus 1. Now, we earlier saw n was 7, so that means n minus 1 is 7 minus 1, or 6. So next we take the number that we just found, divide it by n minus 1, or divide it by 6 in this case, and we get 18.905. What do you do in the final step? Once you've found this number, the final step is to square root that number in the calculator. So 18.905, take the square root, and we get 4.34798. Let's round that to 3 decimal places. 4.34. Okay, after the 7 comes a 9, so we should round the 7 up to an 8. So this will be our standard deviation. So as you can see in these last examples, there are quite a few steps to find the standard deviation. But in order to help us go through those steps, we can use this nice table method to organize our thoughts, and then just make sure you keep this list of steps handy as you do your homework. And then remember that this will be provided on the exam, so that you don't have to memorize these steps, you just have to know how to work with them. So if given these steps, you should know how to work with the table that you create. You calculate the mean. Well, first you make the table that lists out the data values, the deviation from the mean, the square of the deviation. Then you start to fill in the table by calculating the mean. Then you can find the deviation from the mean. And then you can square each deviation. Then you have finished completing the table, so what do? You add all the third row elements together as we did in our previous example. That's the sum of the deviations. You'll get a single value there. Then you divide it by n minus 1, where remember, n is the total number of data items in all. So subtract the total number of data items by 1, and you divide that by the number you just found. And then you're almost done. The final step, you would take the square root of the value you just found in the previous step. So now that we've gone through a few different practice problems of finding standard deviation, the last definition I want to introduce to you and the formula is that of variance. Now, the formula for variance is really quite simple once you have standard deviation. If you have standard deviation, then the only thing you need to do to find the variance is take the standard deviation, square it, and that will give you what we call variance. So in this example, we're told that the standard deviation has been calculated to be 7. What then is the variance? We know that if we found standard deviation, in this case it was given to us, if we square standard deviation, that gives us the variance. So the variance in this case is 7 squared, which is 49. Welcome. Let's begin with properties of the normal curve. In statistics, data can be presented as continuous random variables, and one important type of random variable distribution is the normal distribution. A distribution is said to be normal if its graph has the characteristic shape, like a bell, and symmetric around the mean, median, and mode. In a normal distribution, in the very middle of the distribution, at the peak, lies the mean, median, and mode of the data set. So in a normal distribution, the mean, median, and mode are all equal values. Let's review some properties of normal curves. As we mentioned earlier, in a normal curve, the mean, median, and the mode of a normal curve are all the same value, and they all occur at the center of the curve. Now, due to the normal distribution's particular shape and properties in relation to the mean, median, and mode, the empirical rule tells us where certain percentages of the data are guaranteed to lie. For normal distributions, about 68% of all data values in the normal curve lie within one standard deviation of the mean in both directions. Let's look back at the graph to get a visual of what this means. We learned in a previous lesson how to calculate the standard deviation. So for this particular graph, let's say that this distance is exactly one standard deviation. And we see that we're basing it off of the mean. Now our definition said it lied within one standard deviation in both directions. So we would also have the same distance to the left of the mean. So 68% of the data values lie in this range. Now, if we instead go out 2 standard deviations from the mean in both directions, we see that 95% of all data values lie within 2 standard deviations of the mean in both directions. And if we continue to go out further, if we look 3 standard deviations from the mean in either direction, 99.7% of all data values must lie within 3 standard deviations. So seeing this on our graph, so in conclusion, if we know that we're looking at normally distributed data, then we know that a certain percentage of the data must lie within 1, 2, and 3 standard deviations of the mean. So 95% of the data must lie within 2 standard deviations of the mean in either direction. In this next example, we're told that 300 students have taken a midterm exam, and the distribution of their scores can be treated as a normal curve. Now this is a first key phrase, which tells us we have a lot of things that we can assume about this distribution. Let's list those out. Once we're told the distribution is normal, we can immediately assume, based on the definition, that the mean is equal to the median, which is equal to the mode, and additionally, the empirical rule applies. And the empirical rule, as we saw in our previous slide, is that 68% of the data values lie within one standard deviation of the mean in both directions, 95% of all data values lie within 2 standard deviations in both directions, and finally 99.7% of all data values lie within 3 standard deviations. Now we are asked, based on this information, to find the number of scores that fall into each of these categories. The first one is within 1 standard deviation from the mean. So in order to determine this, we need to go back to the empirical rule. Let's look back at that information. In the empirical rule, we were first asked how many lie within 1 standard deviation, and we see 68% of all data values must lie within 1 standard deviation. So based on this, we know that of the 300 students that are in our data set, 68% of the 300 students must be within 1 standard deviation of a mean. We know how to take the percent of a number. We first move the decimal place on the percent 2 decimal places to the left, and then you take that new value in decimal form and multiply it by the original value. So we want to multiply this by 300. Let's type this into our calculator. And we find that 204 exams must lie within 1 standard deviation of the mean. Now, our next question is quite similar. We still have the original 300 exams, but now we're curious how many of those exams would lie within 2 standard deviations of the mean. And my hint to you is we're going to use the empirical rule, except now it's just what's the percentage of data that's guaranteed to lie within 2 standard deviations of the mean. So I would encourage you to pause the video right now and attempt this problem on your own, and then unpause to check your work. Now we know by the empirical rule, which fits normal data sets, that 95% of all the data values lie within 2 standard deviations. So I just need to calculate how many of those 300 exams would account for 95%. So we're asked to find 95% of 300. As before, we first turned the percentage into a decimal and then multiply by the original value. Let's type this into our calculator. And we see 285 of the exams lie within 2 standard deviations. Let X be a particular data item in our sample. And in this data set, we know that it has a mean, which is represented by X bar, and a standard deviation represented by S. Then the formula for the z-score in regards to X can be calculated as follows. The z-score of X is equal to the data value minus the mean, then divided by the standard deviation. So this will be one of our important formulas going forward. Let's see how the z-score is used. In this next example, 2 friends, student A and student B, are in different classes and they both took midterm exams. Now, since they're in different classes, there was different exams and different students who took the exams. We are told that student A's score was 86 and student B's score was 78. Now, if we were just to compare student A to student B's score, student A did score higher, right? 86 is higher than 78. But since they're different classes, we can see that perhaps one exam was harder than the other, and we could maybe base that understanding relative to how the rest of the class did on the exam. So for instance, maybe in student A's class, everybody scored higher because the exam was potentially easier. Or in student B's case, maybe other people did score higher and they just scored a lower score. We can answer that question if we look at the students' relative z-scores, which then considers the overall behavior of the class as a whole. So we were asked, based on z-scores, which student did better given the class's data shown below. Now, a z-score measures how many standard deviations the value we're looking at is away from the mean. So in order to see who did better, the more standard deviations you are away from the mean in the positive direction, then that means the higher your score was. So this question is really asking us, who has the higher z-score? Whose exam grade is farther away from the mean than the other? Now we can do this with 2 z-score calculations following this formula. Now in the chart, we are told the mean. So we have 13 divided by 8. And we get a z-score of 1.625 for student A. Now I would encourage you to... Now let's take a moment to write down what this means. So for student A to receive a z-score of 1.625, that would mean that they scored 1.625 standard deviations above their class mean score. And let's contrast that to student B, who had a z-score of 1.8. That means they scored 1.8 standard deviations above their class's average score. So even though numerically 86 is definitely higher than 78, whenever we consider the z-score, which kind of standardizes it for how the other students did in the class and the standard deviation of their performances in the class, we could say that comparably, student B scored higher relative to their own class because they scored 1.5 standard deviations above the mean when compared to other students in the class. So our answer to this problem is that student B did better when compared to their class overall performance. And we know this because student B's z-score was higher than student A's z-score. Our next topic will be percentiles. If approximately n% of items in a distribution are less than the data value x, then x is said to be in the nth percentile of the distribution. And we would write that as the nth percentile, p subscript n. Let's explain what that means in a context we might have heard before. If you scored in the 73rd percentile on the SAT, so that would be written as P73, this means that you scored higher than 73% of all people who took the SAT at that time. Now, does this necessarily mean that we got 73% of the answers correct? The answer to that is no. It doesn't tell us how many answers we got correct, it just tells us we scored higher than 73% of the other participants. Now we can apply this understanding of percentiles to actual data sets. So in this example, we have numbers of dinners at a customer, the numbers of diner customers served by a restaurant on 40 consecutive days. And we have been told that this list has already been reordered in least to greatest, so we don't have to worry about that here. We're asked to find the 65th percentile. So if we were to write that in our particular notation, we know that's the 65th percentile. And that would be what value is higher than 65% of the other data points. Now, since things are already listed in order, all we need to find is what is 65% of the 40 different positions listed in order, and then that will be the location of our data value that is higher than 65% of the other data values. So here we're going to find 65% of 40, not to find the 65th percentile itself, but to find its location in this list of 40 numbers. Percentage of a number is always turn the percent to a decimal place. So we have 0.65 times 40. We'll type that into our calculator, and we get 26th. So the 26th place out of 40 represents up to 65% of the data values. So in order to get above that, because we know we want to be higher than 65% of the data values, we'll need to go to the next entry. And now that we know its location, we can just carefully count. We see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like each row is 10. So we have 10, 20, 21, 22, 23, 24, 25, 26, 27. So this is the 27th location in the list. So the number 68 is higher than 65% of the other data values. So our 65th percentile is the value 68. So keep in mind here, we knew how many data values there were. So we use the fact that it needs to be higher than 65% to find the location in the 40 data points where we were exactly at 65% of the data. So we found 65% of 40, that was 26. So digits 1 through 26 comprise exactly 65% of the data. So the next score over is now higher than 65%. Now for the same example, we're asked to find the 88th percentile. So this is very similar to the problem we've just done. So that you can practice, I'd recommend you pause the video now and attempt this one on your own, and then unpause to check your work. So here we have 40 data values. In order to be in the 88th percentile, we need the data point that's higher than 88% of its peers. So we'll first find that location in the 40 data points. So I'm going to find 88% of the 40 data points. Now that would be turning the 88% to a decimal, multiplying it by 40, and we would get 35.2. So the 35.2th position in the 40 values is higher than 88% of its peers. So based on this, we know the next term, so one higher than 35.2, which is the 36th term, will be higher than 88% of the other values. Now we can either count up to 36, or since this is an order and we know this is the 40th position, then this would be the 39th, this would be the 38th, 37th, and then 36th would be counting back 4 from the end. So the 80th percentile is the value 75. Our next topic of this video is finding quartiles. So we have a few definitions to read over at first. The second quartile, which is written out as Q subscript 2, is always just the median of the data values. So keep that in mind. You always find the second quartile first, as it's the median of the data values. Next, we have the first quartile, which is written as Q subscript 1. And the way you would find it is the median of all values below Q2, the second quartile, or below the median. So once we find the median of the data values, that splits us into half the data values are below, half are above. So the median of that half below becomes the first quartile, and then the median of that half above the original median becomes the third quartile. So we can see how to find this in this next example. We're asked to find the three quartiles, Q1, Q2, and Q3. Now keep in mind that we'll always want to find Q2 first because it enables us to find the first quartile and the third quartile. And Q2 is just the median. So in this data set, it says it's the same from the last example, and we knew in our last example these were listed in order. So we could visually check, but we can go off the fact that we knew these are already in order. So to find the median, I just have to find the exact middle. So as we know from our last example, there's 10 in each of the rows. Consider the first 10 numbers cancel out with the last 10 numbers because we're finding the middle. And now we can work the remaining least, the remaining highest, and just work our way towards the middle value. Of course, we could also understand where the middle would have to be, and that might shorten our work, but this will always work as well. And as we continue to work our way towards the middle of the data set, finding the median, we see that we're left with two values. And that makes sense because since there's 40 terms, we know anytime there's an even number of data values, we'll have to average to find the median because there's no single middle value. So in order to find the median, since we have 2 in the middle, we know we just average those two numbers. So that's 65 plus 66 divided by the fact there's 2 of them. And that will get us the value 65.5. So that's our second quartile. And now as we look at the definitions above, we see that the first quartile is the median of all items below Q2. Well, if Q2 is 65.5, then all items below Q2 belong to this group. So in order to find the first quartile, now that we've identified all the data items below Q2, we just find the median of this new set of data. So take out the lowest, take out the highest. Take out the next lowest, take out the next highest, and we'll just continue this process until we work our way towards the middle. And since there's 20 items here, we expect that we'll have to average once we find our middle values because there's not a single middle. So the second quartile would be 59 plus 60 over 2, and that will get us to 59.5. Now the definition for the third quartile is for all the items above Q2, find the median of that new data set. Now I would encourage you to pause the video and attempt to find Q3 on your own. And then when you've completed your work, unpause and check your answer. So we see the data values that lie above the median are all the values higher than 65.5, which are these 20. So all we have to do is find the middle of these two terms. Now we know there's 20 terms in all, so halfway between will be the 69th and the 70 term. And as we're trying to find the median and we end up with 2 terms in the middle, as before, we know we can add them together and divide by 2 to get our median value. And we'll find the third quartile is 69.5. So just a quick review of this type of problem. We've got 3 new definitions: the first quartile, the second quartile, and the third quartile. Whenever we're asked these types of quartile problems, we need to remember that we must first find the second quartile, because the second quartile is what everything else is based off of. And keep in mind, the second quartile is just the median. Once we've found the second quartile, then that separates the data values into items below and items above. And in those 2 new lists, you just find the median of the items below and that's Q1, and then the median of the items above, and that's Q3. So whenever you do the quartile problems, remember to start and find Q2 to begin with. Now that we know how to find Q1, Q2, Q3, our three quartiles, let's introduce one more definition. The IQR, which is an acronym for the interquartile range, can be found by taking Q3 minus Q1. So for our example above, the IQR here would be found by taking our Q1 value of 69.5 minus our Q1 value of 59.5. And we get that the IQR, the interquartile range, is 10. So if you're ever asked for the IQR or interquartile range, remember you first need to calculate Q1, Q2, Q3, and then take the Q3 value minus the Q1 value. Now, our last focus will be using the IQR, so the interquartile range. Once we can find this, we can then use it to identify outliers by the formulas here. Let's zoom in for a moment. If we know the IQR for a data set, then the lower outlier boundary is the Q1 value minus 1.5 times the IQR. The upper outlier boundary is then the Q3 value plus 1.5 times the IQR. Now we have this word for outlier. Outlier in our data set are data sets that are far away from the general behavior in the data. And the way we can find these outliers is through these formulas, because any data item that is below the lower outlier boundary, as described by this formula, or any data value that is above the upper outlier boundary, is then said to be an outlier. So for our previous example, let's calculate the lower outlier boundary, the upper outlier boundary, and then using those boundaries, let's determine if any items in the data set could be said to be outliers. So our lower outlier boundary, we know Q1 is 59.5 minus 1.5 times our IQR from the previous step was 10. So let's type this into our calculator and we will see what the lower outlier boundary would be. The lower outlier boundary is 44.5. So data values that are below that are considered outliers. Let's now calculate the upper outlier boundary. It says you take Q3 plus 1.5 times the IQR. So we have 69.5 plus 1.5 times 10. We'll type that into our calculator. And we find that the upper outlier boundary is 99.5. So what this means is any values that are below 44.5 or above 99.5 are outliers for the data set. So let's look at our data set here. Let me erase some of our previous notation. We can see that the lowest data value is 46, which is above the cutoff 44.5, and the highest data value is 88, which is below the cutoff 99.5. So our conclusion here is that there's no outliers, because none of the data values were below the lower outlier boundary or above the upper outlier boundary.